So where I'd like to start today is by giving you an overview of what I'd like you to be able to accomplish by the end of this session. So at the end of the session, I'd like people to be able to walk away from this session and be able to summarize to somebody how people learn, give them a brief overview. I'd like them to be able to apply at least 2 teaching strategies to redesign or design a new upcoming lecture. And then I'd like them to ultimately be able to map those 2 strategies that they selected back to their summary of how people learn, essentially justifying why they chose those 2 topics. Obviously, more would be great, but I understand that these things change as a process. And so I think 2 is a good number that most people can probably wrap their arms around with and get going with in the classroom. So to give you a little bit of a sense of where we're headed with this, I think we're going to divide the lecture into 2 parts. The first part will be focused out here in the audience of the lecture. We're taking a look at the students and looking under the hood, so to speak, of the learning process to see what's going on out there. And then the second part of the lecture will be focusing in on the instructor, trying to get a sense of how the instructor might take advantage of this understanding of the nature of cognition to optimize instruction in a way that really does foster student learning, especially in the format of lecture. So, ironically, this May, NSF released a nice press release about a meta-analysis that was conducted by Freeman et al., taking a look at the role of several instructional strategies in undergraduate STEM classrooms. In particular, this study was looking to test the hypothesis that lecturing maximizes learning and course performance. And as you can see from, get a hint from the headline of the press release from the National Science Foundation, they found that their hypothesis was false. This was a meta-analysis of 225 studies in undergraduate STEM courses. And specifically what they found was that active learning increased exam scores or scores on concept inventories by approximately 6%, or an average of half a letter grade. This was an effect size of about 0.47 standard deviation. And they also found that while that was the average effect, the effect was unevenly distributed. And actually, the greatest benefits went to the students who were who were lower performing. Here, students that were in the 50th percentile could experience gains as great as up to moving from the 50th percentile in a traditional lecture class to something like a 68th percentile in the active learning scenario. And perhaps more importantly, or measured another way, they also found that students in these traditional classes were 1.5 times more likely to fail the course overall as their peers that were in active learning settings. So I think it begs the question, with this study coming out, why are we even going to start talking about lecturing today? So to get a sense of this and begin the conversation, build onto that question, I thought we might begin by taking a look at this comic strip and take a look at, I'd like everyone to take about a minute or so and think about what this says about learning. And Danielle, once we kind of go about a minute or so, I'll ask people to maybe start typing in some of their responses into the chat window, and maybe you can start reading some of them out to me when we get to that point.
Sounds good, Michael.
So hopefully this only feels like an odd pause to me because I'm out here and hopefully everybody's jotting down some ideas. Why don't we go ahead and open it up to the chat window, and if people have some thoughts about what this cartoon might say about learning, why don't they go ahead and start typing them in.
Getting a lot of good responses. Wendy Williams says that it gives the reality that we perceive it's taught just because we did the usual. Sage of the stage.
Mm-hmm. Yep, that's a great perspective.
Rob Porritt says, you can teach a dog to whistle, but you can't make him sing. Like the old analogy to leading a horse to water, but you can't make him drink. There's also an element of I can do everything right, with quotes around right, but it's still having no impact if I don't pay attention to the learner.
Sure. Mm-hmm. Okay.
What's his last name? I'm going to butcher your last name, but Benjamin Van Wyck de Vries. Sorry. Exactly the comment I get from some colleagues who accuse students of being stupid because they don't learn from the lectures. The students also feel that.
Mm-hmm. Yeah, very powerful.
Robin Kronwitter says teaching is reciprocal. Information can be given, but has to also be received to be truly teaching.
Right. Okay. Great. That's a good snapshot of ideas, and I hope everybody benefited from getting to hear some of the other participants' thoughts about this.
Yeah.
I kind of jotted down some of my own thoughts to share with the group, since I didn't know if we'd be able to see everybody or have a time to necessarily get through everybody during the webinar. But some of the ideas that came to me was that sometimes the instruction and the assessment must be better aligned. And in this particular case, if we flip back and look at the cartoon, the assessment is a performance assessment. They want to hear him whistling, and when he says he taught him how to do it, he didn't say that he learned it. Well, there's no specificity in terms of how he taught it. He might have misaligned his instructional strategy, and maybe he simply gave a lecture on how one might go about whistling or the physics of whistling, as opposed to giving him an opportunity to practice. And that kind of leads into the next idea I thought about, was that lecturing is not one size fits all, that there are some concepts and certainly some outcomes that you might want to cover that lecture just isn't going to fit no matter what you do. So like all things, there is the right tool for the job, and in some cases lecturing is just not the right tool and it shouldn't be used. I would also argue, and this is, I think, one of the ones that somebody alluded to, was simply giving out the information isn't enough. Telling isn't necessarily teaching. And really, for learning to take place, and I think this is the reciprocal portion of it that somebody else had mentioned, that information needs to be organized and practiced for it to really become understanding, to go beyond just a collection of facts, perhaps about how one might be whistling, and really take it to the level of having it become student understanding or learner understanding. So I think I would, maybe we can build from this idea in the sense of what learning is. You know, the traditional lectures, which have been around for such a long time, worked much better when the expectation was simply that most people would learn to read, write, and perform some calculations, especially when we had a period of time when people didn't know how to read, and so we had an illiterate population. Lectures could be effective. But as the Nobel laureate Herbert Simon noted, this meaning of knowing has shifted from being able to remember and repeat information to now where we need a population that's able to find and use and apply new information. So I think the question that we're really after today is, how do we achieve learning that's understanding through an instructional pedagogy that has been used since at least the Renaissance era, right? What can we do to modify lecture to really help students develop understanding? So I think what we need to do is begin by examining what we know about the learning process. What's the nature of cognition? So let's begin by taking a look under the hoods of our learners. We know quite a bit about the learning process from a collection and history of empirical and theoretical studies conducted by cognitive psychologists and educational researchers. And more recently, this has been supplemented by the rapidly growing field of neuroscience. But let's begin with some of the feedback and the information that we've gotten from cognitive psychology. I think the first premise that we need to build on is the idea that, unlike Gilbert's coworker here, students aren't empty vessels to be filled with information. And Carl Wyman, a physicist, Nobel Prize-winning physicist who's now doing quite a bit of educational research, especially within the realm of physics education, has sort of summarized this collection of research around educational cognitive research with this basic principle that people learn by creating their own understanding. And so this first idea that we're after, that people aren't empty vessels to be filled, is really an important one that we have to keep in mind. The next idea is that not only are they not empty vessels to be filled, but that this prior knowledge that they come with includes experiences, cultural context, other ideas that they've learned from other places, all of which that must be accounted for as part of the learning process. And an example of this that's really well done is a story called Fish is Fish. And two of the illustrations are on the screen. I just read this to my daughters, 4 and 7, last night, who were thoroughly entertained with it. But if you're not familiar with the story of Fish and Fish, it kind of goes like this. There's a fish and a tadpole that live in a pond, and they're best friends. They grow up together, and over time, the tadpole begins to lose its tail and sprout legs. Meanwhile, the fish continues to grow larger and larger. And eventually, the tadpole is no longer a tadpole. It's fully achieved its legs, lost its tail, and hops from the pond and goes out to see the world. The fish continues to grow and become a full adult fish, while the frog is out exploring. And eventually, the frog comes back to the pond to visit with the fish. And the fish asks the frog where he's been. And the frog proceeds to describe to the fish everything he's seen while exploring the wide world. And as you can see illustrated here, the frog describes birds to the fish, winged birds that have 2 feet and can fly in the air. He also describes to the fish spotted animals that give milk and are very large, as well as humans which wear clothes and walk upright and have 2 legs and also have hands. And so you can see in this sketch that the fish is very strongly influenced by his own personal experience about what is out there in the world, and his perception of what the frog is telling him is very strongly influenced by this. And we find this all the time within the learning field. When we're working with students, their prior knowledge, their experiences, their cultural context are really important and powerful. The next thing that we know about learning is that students must actively participate in the process of organizing the information that they take in. It isn't enough to just simply hear it, but this information must be assimilated into this prior knowledge in a way that makes logical sense. We might think about it in this way. This is some of you may have seen this quote before, but the idea that science is constructed of facts as a house is of stones, but a collection of facts is no more science than a heap of stones is a house. In this way, students have to organize their learning not only so that information can be retrieved very efficiently, but it also helps them make sense of the world around them. And more importantly, they can then use this information to make predictions about new information that they'll encounter in the future. And so this is part of the active process that students go through when they encounter information, is sort of integrating this in order to really learn it and have an understanding developed from it. Another fundamental concept that's related to this about learning is that we know that creating opportunities for students to retrieve information, both in the form of formative assessments, sort of quizzes and exams that we might give along the way, classroom worksheets, study guides, as well as summative assessments, things, formal exams that we give at the end of the semester, all create these opportunities to have students retrieve their information, the information that has been conveyed to them. And so the more often that students are asked to retrieve this information, the more they learn the information. And so it's important that we include both formative and summative assessments while we're thinking about our instruction. So another fundamental principle of learning that we need to be aware of is that students' learning is most efficient when they're actively participating not only in organizing and synthesizing their learning, but they're actually monitoring their own learning. This is an opportunity for them to reflect and recognize when they understand something and when they need additional information in order to fully grasp the concept. Sort of looking into the mirror. This is often referred to as metacognition. In addition, while they're thinking about whether or not they understand a concept, they also need to be aware of the affective domain as well. How are they feeling about things? Students who are fearful or anxious, depressed, can't focus to process the information that's being presented to them. And related, students' positive feelings, their confidence or self-efficacy, can actually have powerful influences on their ability to persevere in the face of difficulties when they're struggling with complicated problems in the classroom, struggling with concepts, and that sort of thing. Students' sense of their ability to be successful really can have powerful impacts. And related to this, is also the idea that not only is it important that students work with them, work internally to assess their own understanding, it's also very important for us to provide social opportunities for students to assess their own learning. This is the chance for students to interact with one another and talk about and explain the concepts that are being presented to them. We see this frequently that this provides great increases in students' learning when they're presented with these opportunities to both be forced to explain something, but also take into account others' conception of the concepts under study. And so this social construction of knowledge is something that we see over and over again throughout the literature. And a final sort of concept that we want to emphasize here is that students have a number of intelligences and skills in a number of different areas that go beyond the standard language and mathematical abilities that are typically emphasized in schools. These are spatial skills, musical skills, kinesthetic abilities, and students demonstrate differences in how they prefer to take in and process information based on these skills. And as a result, we know that by providing students with different opportunities to explore and express learning in a variety of formats can help increase the learning process for a number of students. Now, one caveat I would give here is that when we talk about students having a number of different intelligences, we've seen tests that have been around for the past sort of decade or so that students test as to what kind of learner they are. And I think that we need to be cautious about that, in that these are a spectrum of skills, and students have skills in a lot of different areas. And so we want to emphasize to students that while they may be slightly stronger in some areas, all areas can be developed and emphasized. And in fact, we might even be encouraging students to work to develop skills in areas where perhaps they aren't as comfortable all the time. Okay, so I'd like to pause the conversation for about a minute, and I would like to give you a chance to sort of reflect on some of the ideas that we've talked about so far. This might be the question of the study, the meta-analysis at the beginning related to lectures, perhaps the cartoon that we looked at, or perhaps some of these fundamental ideas that we're getting from about the learning process that we're getting from educational research. So just take a minute and pause and jot down a few ideas. Give you maybe 30 seconds or so. And you might also expand some of the ideas that you're jotting down to include maybe some questions that you have, a question that's still lingering for you. Okay. It's a little tough for me to not be able to see whether people are still jotting ideas down or not, but it's been about a minute, and there's no need for us to type these in. This is really to help you sort of frame your own thinking about this presentation. So I'm going to go ahead and move on to this next piece. So the next component that we want to focus on is some of the feedback that we've gotten from cognitive psychologists about what the theoretical construct for the brain might be in terms of how we learn. And one caveat I want to give before we get into this is that what I'm going to discuss is not referring to specific areas of the brain. We've all seen mapping of the brain before, where we know that there's a musical sort of skill area. There's an area where speech and language is centered. There's all these different centers of the brain. And what we find is that initially we thought that there was also an area for things like short-term memory and long-term memory within the brain. But the study of neuroplasticity has really helped us see that these ideas, these theoretical constructs, actually apply across all of the brain. So these constructs that I'll be discussing actually affect all areas of the brain. And we call this the multi-store model of memory. And it starts off with, on the upper left-hand side here, with inputs into what we call sensory memory. And I've just chosen two sensory systems here to list because they're the two that are most common for an educational setting. But this would be visual and auditory, visual, verbal, and auditory. Would include taste and smell and touch and a variety of other senses as well. This is the shortest type of memory that we have, and on average, this memory is forgotten in 1 to 3 seconds because our bodies are constantly bombarded with sensory memories. And so we need to be able to push these out in a pretty rapid time. The second area of memory that we'll take a look at is what we call working memory, and sometimes this is referred to as short-term memory. And there's quite a bit of debate within the literature right now about what the difference is between these two areas, whether working memory and short-term memory is the same, whether they're two different components of the same thing. There's quite a bit of debate. There's studies that use the terms interchangeably in them. In fact, just a year or two ago, there was a really nice theoretical piece out on several different potential models for the relationship between working memory and short-term memory based on some of the empirical evidence that we see through a variety of studies. But in general, we do know that there's this sort of short-term working memory system that's in place. And memory here lasts on the order of 15 to 30 seconds before it's forgotten, give or take. This is where we might store things temporarily. And you might think about this in terms of something like looking up a phone number and then picking up your phone in order to dial it. You can teach yourself to remember those 7 digits for a short period of time, about the time that you've dialed it and somebody answers on the other end and you start the conversation. That information is pushed out of your mind. You haven't needed it anymore. That information is now forgotten. What we know about the working memory is that it has separate processors for different types of information. And it's important to note that these processors are finite. They have a limited capacity to them. And you may have heard there's been a number of NPR stories over the past year or two about the amount of information that we can bring into these processors before they become overwhelmed. And on average, we think about 7 or 9 chunks of information being about what an average person can hold in their working memory at any one particular time. This is also why strategies like mnemonics are really effective. Whether we want to remember the colors of the rainbow, Roy G. Biv, that helps us because now all of a sudden we've taken all those colors of the rainbow and we've chunked them, we've brought them down into one component that we only need to bring into our working memory at a time, which helps free up more working memory for us to process additional ideas. So important to this concept of lecture is the idea that we have a visual processor and we have a verbal and auditory processor. And we'll be talking about more about those more in a little, I guess, a few slides. The third component to this is the long-term memory system. And this is where we're going to permanently store all of our knowledge and skills. And the capacity for this, we believe, is unlimited. There are no signs that anybody's filling up their long-term memory within their lifetime. And some long-term memories can be dumped in short of in a second, but for the most part, these are memories that are going to last for the duration of our lives. I think what's important to note here is this back and forth connection to the working memory. This is where when we're processing information in our working memory, we have this process where we can encode the information or move it out of our working memory and into our long-term memory. And we know that there are some active techniques that can help us. This is practice, rehearsal. You might call it cognitive processing, where students are thinking about the concepts, making connections to new ideas, and also they're also pulling they're retrieving information from their long-term memory and feeding it into their working memory with their new ideas and making sense out of the new idea as it relates to their existing hierarchy within their long-term memory. And if they're able to complete that process, that analysis of this information, that information is more likely to be encoded and passed on to our long-term memory. And so from our perspectives as instructors, this is a really important thing, and it's something that we want to make sure students have both the time to do, but also we're providing the instructional opportunities for students to actually work on that encoding process. And so the next piece that I wanted to focus on is what we get from neuroscience. One of the things that we've learned from neuroscience is that what we're after when we're teaching students is change in our students. And by this, I don't mean change in attitude or behavior, although that may result from the change that we want. We really are talking about physiological changes to our learners. In this case, these physiological changes are taking place in the nerve cells called neurons that are in our brains and in our nervous system. Neurons are specialized cells that are designed to carry messages through electrochemical processes. And as students learn, these neurons physically change, create new pathways, and in some cases, as information is no longer used, pathways may be trimmed back or managed, manicured, so to speak, so that they are optimizing the connections that take place. And where these connections take place are out at the ends of the neurons. They have specialized projections called dendrites and axons, and the dendrites are bringing information into the cell body, and axions take information away from the cell body. And the actual flow of information from one neuron to another occurs across a synapse. And a synapse consists of neurotransmitters and neuroreceivers on either end of these synaptic endings, and in between there's a synaptic cleft, or a small space between the two. And so we actually see the neurons growing new synapses when they are creating memories. So the way that we believe this works is that when short-term memories, which are temporary and reversible, as we've just seen from the theoretical model, we think that this is achieved through electrical or chemical changes that are occurring at synaptic endings. And this has been described as the synapses vibrating across the brain. However, because it's temporary and tentative, nothing permanent happens there. However, when encoding occurs and students actually commit this information to long-term memory, this is when we begin to see physical and chemical changes to the neural pathways and the synaptic connections. We see more of them connecting, and we're also seeing not only are they connecting between neurons that are next to one another, but we actually see pathways being constructed through the hippocampus, which serves as sort of a switching board for the opposite sides of the brain to be able to make connections to one another. So we might be connecting from our sort of mathematical logical processing side to sort of other areas of our brain, and this is happening to the hippocampus. So an opportunity for us to actually make physical changes, which then would be translating into those attitudinal or behavioral changes that we see in our students. So to kind of give us a way to think about this, I'd like you to take a look at this video that I'm going to show. And before I begin to play it, I want to give a brief description of it. So this is an acrylic box, cube actually, and the acrylic cube is filled with mineral oil. And in the mineral oil, you can see iron filings. And through the center of the acrylic box, you can see that there's a tunnel. So a box filled with mineral oil, suspended in the mineral oil is iron filing, and there's a tube that extends through the center of this box. And what we have is a magnet here, a magnetic rod that we're going to insert into this tube through the center of the box. And I'm going to pause the video for a second. And what I'd like everybody to do is to take a moment and predict what's going to happen when the magnet gets inserted into this box. Okay, that's, most of you probably know what's going to happen. So let's see what actually occurs. But as you're watching it, what I'd like you to be thinking about is how might this work as an analogy for generating the type of learning that we seek? And you might also simultaneously be thinking about how this analogy might not work. So let's go ahead and see what happens when they put the magnet in. Okay. First of all, I think it's just an amazingly cool thing to see in 3 dimensions. I think it's fascinating and beautiful at the same time. So they're going to turn it, she'll turn it one more time. We can see at the end here, look down at the end of the magnetic field. There you can see it edge on. So I'm sure that was pretty similar to what most of you were expecting to happen. Now what I'd like you to do is take a moment and think a little bit more deeply about that idea of, could this be an analogy for generating the learning that we're interested in, based on our discussion of both the theoretical and empirical evidence for the learning process, as well as the neuroscience evidence that we've seen through being able to peer into the brain. So we'll give you about a minute to do that. And as you're coming up with ideas, you can also put those right into the chat box, because I'll ask Danielle in about a minute to read some of those out. Okay, hopefully people are typing some things in. Danielle, are we getting some ideas offered in the chat window?
I mean, a couple.
Okay.
Caroline wanted to mention that she did this exercise with her her physics of the earth class last spring, and she said it was really successful. So
wonderful. Now, I'm guessing she used it in her physics of the earth class more about the magnetic field than she is about how it might be an analogy for learning.
Right. But yeah. So Karen Luttrell mentioned, she says in a question, learning requires a magic wand.
Right. So perhaps that's not a good, perhaps this isn't a good analogy, and that you have to have a magic wand. Okay, great.
Patrick McQuillan says the magnet has to remain in place for the filings to show the pattern. It's analogous to a period of time, repeating, reviewing, etc., for the pattern or learning to stick. If you put the magnet in and remove it quickly, the pattern forms and then goes away.
Right, right, excellent. Right, great idea. Okay, I offered, came up with a few ideas here too.
Michael, we have a few more too. A couple more people wrote in. Wendy Williams says, analogy, the steps we discussed provides that alignment in teaching and expected true learning we strive for. However, another aspect is that it does demonstrate the polarizing effects when we don't actually execute our processes effectively. So still a polarization and disconnect. Rob Porritt writes, I'm still thinking about how different people learn differently. So in a sense, identical iron flakes are a poor analogy to students, but the end where she shook it up a bit makes the analogy a bit better.
Okay, yeah, right. Great. Yeah, those are all great ideas. And there were many of the ones that I actually thought of too when I was thinking about this. In some ways, I thought it was a good analogy in that, students' thought processes could be like the magnet that over time organizes the content. I think Patrick had mentioned that idea about time, that the longer you leave it in there, the better the structure becomes. And I also thought that somebody had mentioned about shaking the box. I thought that was a good analogy of the role of the teacher of becoming, interacting with the mind of the student. I thought one of the ways that it could not necessarily be a great analogy is that that students could passively, absorb an organizing theme to knowledge. Putting the magnet in and it's good enough. And I also thought the idea that it was the closed system with no new filing, for example, being added to it. Great. So I think that we're going to move on to sort of part 2 now. We've gotten a sense of what might be going on under the hood for our learners in class. And now we want to think about how the instructor can, how he or she can optimize their instruction in a way that is going to bring about the type of learning we want. So I mentioned this quote earlier, and I wanted to show how Carl Wyman goes on to further emphasize the role in the instructor in this process. He says that not only do people learn by creating their own understanding, which is really important, but that it does not mean that they must or even can do it without any assistance. It's important to keep in mind that what we're talking about are novice brains, that these are brains of students who need people to coach them and to on how to think about their own thinking, how to ingest and organize information, and how to persevere in situations or difficulties that they might face during the learning process. So, how do we get started designing instruction, in this case a lecture, that's informed by the nature of cognition? Well, one of the places that we start is with this idea of backwards design. And I'm not going to go into backwards design too deeply. I will mention that backwards design is exactly what it says. It means you start at the end and you work forward. You begin by identifying the desired results that you'd like from your learners, and you determine acceptable evidence for that, and then you plan the learning experience. I refer you to a great talk that David McConnell gave as part of this lecture series, and 2 years ago now, about getting ready for class, and it was a fantastic talk, and he goes deeply into the idea of backwards design and the relationship between curriculum instruction and assessment, and I think it's one that everybody should take a look at. But what I will do is I will bring up the way I use backwards design. In this case, I started out my planning for this seminar by stating what I wanted you to be able to do. And I mentioned it again now, and by bringing it up again, we can see how it's also useful for supporting and encouraging that metacognitive processing. So at this point, can you summarize how people learn, or at least provide some basic oversights about some of the key ideas for how people learn? Can you apply any teaching strategies yet? And can you map those teaching strategies back to the summary of how people learn? And so I'd like, hopefully, you've been encouraged to think a little bit just by seeing these again and having them brought forth partway through the instruction about what your own learning has been so far in this session, and perhaps what you need more information on in order to achieve the outcome. And as we mentioned, this is focused on lecture, so I'd be remiss if I didn't include at least a brief mention of the dangers of doing this during lecture. And I see this all too often when I walk past classrooms. Here's a whole bunch of stuff that I want to talk about, and I'm going to provide you with a bulleted list, and I might actually read these all to you, or I may put this up and I may really only talk about bullet number 3, and I'm not sure which of those two scenarios is actually better or worse. But it's worth mentioning here, because you'll remember from previous slides that learners possess this dual processing system where information is brought in through separate and finite, very limited systems for words and pictures and or auditory and verbal material. And this means that when we're designing slides, we need to be mindful that text on the slide, text gets processed initially by the visual working memory, and then it gets transferred to the verbal working memory for us to make sense of the language that's being communicated. So that means text on the slides can compromise and be in competition with other graphics that are on the slide or the talking that you're doing during class, because it has to be processed through both the visual and the verbal auditory channels. So when we're designing slides themselves, emphasizing the idea that less is more and right-sizing the complexity and density of information is an important instructional consideration. And I won't say much more than that, other than to mention that Scott St. George, in the spring of 2013, gave a nice talk on how you can enhance your presentations, and he was very focused on slide design. And so he didn't really go into the sort of theoretical underpinning for why these are important skills, but he does give you a lot of very practical nuts and bolts. And so I encourage everybody to take a look at that. And the final thing that I wanted to emphasize in terms of creating instruction that's actually a lecture, but does encourage student understanding, is the introduction of a constructivist learning cycle as the backbone for your lectures. And a number of you will have been familiar with variations of learning cycles. There's been many that have been proposed, and lots of modifications of those that have been proposed. And most, I think, will serve you well. So any learning cycle is a good one to grab onto. And I find some of them better suited for looking over a whole course, for example, or a unit, and I find others are better for individual sort of one-off uses. I like this one for presentations that I'm giving to the scientific community about education for two reasons. First, I think its format and duration fit a lecture very well, and a lecture is a common instructional strategy at the university level, especially when people are dealing with large lecture hall formats. And second, and also it's able to incorporate all of the major components of cognitive theory in it. You know, what we've talked about, as we'll see, fits very well into this idea of opening, prior knowledge, explore and explain, reflect, and apply. And second, I like it because it maps very, very well to the process of science, which is something that most of you as scientists are very familiar with. And so I'll be introducing the concepts for each one of these: open, prior knowledge, explore, explain, reflect, and apply, by mapping from the scientific process to the instructional analog. So let's start with open. The science process, this is analogous to raising the fundamental questions of interest. What is it that you want to do your research on? And this maps very closely to the instructional analog of finding an invitation to learning and leaving students wanting to know more. How do we focus the learning of the students so that their intention and their minds-on activity becomes tied into the content? And here's just a quick example of something that we might use as an opening. This is an example of a discrepant event demonstration where students might be surprised by the behavior of that and want to know more. Or in the case of this lecture that I've given today, we might be wondering why we're talking about lectures when the NSF is releasing press releases that say enough with lectures. The next phase is prior knowledge. And if we think about the science process, this is, okay, now this is the step where, okay, now we've got a research question, and now we're going to take a look at what's already known out there. What does the literature already tell us? And this maps to the instructional analog, assessing students' prior knowledge and making it explicit to the learner. We know that learning occurs when connections are drawn between new knowledge and what the learner already knows. And so this phase of the activity encourages students to recall relevant information out of their long-term memory, bring it into their working memory so it's available for that connecting process. And it also helps you tailor the conversation to match the level of student understanding so that you're not shooting too high or too low with the instruction that you're delivering. The next phase, explore, explain. This is the planning and the implementation of the scientific experiment that you're interested in investigating, right? This is something that, this is sort of the nuts and bolts. And when we map that to the instructional analog, during our during our lectures, this is a time to plan and implement minds-on experiences for the students. Places where you can create opportunities for students to interact with the content in a way that is required for the process of encoding this new information, for them to organize the content into their pre-existing frameworks and encouraging them then to transfer this new information into their long-term storage. In this process, you as the instructor are creating the guide for the organization, and sometimes this will be explicit in the activity, such as maybe you're creating a concept map during the instruction, and other times it might be much more implicit, such as scaffolding the development of a concept through a series of questions. It's also an opportunity for you to encourage students to participate in a variety of modalities. So maybe there's opportunities for writing. Maybe the next time there's an opportunity for the students to sketch something. Maybe the next time they have physical manipulatives that allow them to use their kinesthetic or perhaps even their spatial thinking skills. The next phase then is of the opera sequence is to reflect. And this is the part of the science process where we will reflect on the results and how they affect what was known beforehand. Trying to make sense of these results from our experimentation. And this maps to the instructional process of creating a lecture by providing students to monitor their own learning, or in many cases, socially shared metacognition, how they're interacting with their peers to monitor their own learning. This could occur through formative assessment, pauses during the lecture, allowing time for people to simply process the information that you've presented and ask questions, or using things like think, pair, shares, where they can do something on their own, share the information with a peer, and work together to think about what their level of understanding is. And finally, the last phase is to apply. And this is similar to the idea of communicating the learning via talks and papers, and the fit of these new ideas with the broader ideas that peers have within the science community. How does your science make sense within the realm of what else is out there? And this, of course, maps to our instructional analog of applying the knowledge that they've gained to a novel situation, asking them to recall relevant information and apply it to a new situation. And this is really the hallmark of student understanding. This shows that they have a deeper understanding that's richer than simply a collection of facts. And this might take place through thought questions, model building, showing students models and asking them to assess the quality of them, or constructing their own models, similar as we did in this lab lecture here. Laboratory opportunities where they're exploring new concepts, data analysis, a wide variety of topics could be used here. So to kind of bring this back around to where we started, we began by discussing why we would even be talking about the idea of a lecture when NSF is releasing press releases that calling for enough with the lecture. And I think what they really mean here, and if you read the meta-analysis carefully, what they really mean here is enough with bad lectures. If you look at the inclusion and exclusion criteria for the meta-analysis that this press release is referring to, what we see is that they've got a very broad sense of both the degree and the duration of active learning that's included in those studies. And so in a lot of cases, a well-designed, artful lecture that is built on a learning sequence like opera that activates student attention, that brings up prior knowledge and helps students bring that information forward from the long-term memory to the working memory, allows them to engage with new concepts, have an opportunity to reflect on their learning and apply it to a new situation. I think these sorts of lectures would really have, based on what I can see in the inclusion and exclusion criteria, would really fall within that active learning category that the study had. So I thought, I know we're running a little short on time, but I don't know, homework's probably not normally part of webinars, but I thought in this case it made sense to assign some. One I thought would be to ask people to reflect a little bit on the degree to which this webinar was constructed around the OPERA planning tool, and perhaps we'll want to go back and take a look through the webinar again to see how OPERA was applied here. And two, I'd like you to apply the learning that you've gotten from this webinar to modifying or designing an upcoming lecture to incorporate at least two of the strategies illustrated in this session. So this was one of the goals that we wanted you to accomplish by the end of the session, is to go out and apply at least some of these phases of the OPERA sequence to a lecture that you're putting together. So what I wanted to leave us with is the opportunity to reflect back on this content that we've covered today. So this image is a postcard that was from a series of futuristic pictures drawn by Jean-Marc Courtet, in which illustrated what they predicted France would be like in the year 2000. And these postcards were drawn in 1899 and 1900. And this is at school in France, what they thought this would look like. So I would leave you there to reflect on what this image might say about both the process of teaching and lecturing, and what it says about learning and the role of the learner in the educational process, and how close this vision, which clearly shows the transmission model of education, fits with what we know now and what we're hoping to see and what we do see in classrooms around us.